Welcome to our Quantum Deep Dive. So what if I told you that one of the most important tools for building the quantum computers of tomorrow wasn't dreamed up in some high-tech lab, but was actually written down over 250 years ago?
It sounds kind of crazy, right? But it is absolutely true. Today, drawing from a really fascinating essay by Georg O. Schnippet, we're going to explore how an 18th century equation is, believe it or not, shaping our 21st century technology.
I mean, just look at these two eras. They feel like they're from completely different universes. On one hand, you've got powdered wigs and scientists trying to figure out how planets move. On the other, you have quantum bits and computers that promise unbelievable power.
So what's the deal? How can an idea from way back then be so critical for building the quantum machines of our future?
Well, that is the big question we're diving into. And the answer, as you'll see, is all about this timeless principle of perfect harmony and balance. It's like a secret ingredient that bridges these two completely different worlds. It's a fantastic story of how old ideas can find new life in the most unexpected ways.
All right, here's our game plan. We'll start with the man who came up with the equation, then we'll unpack what it really means, uncover that surprising quantum link, and finally see how it's being used on the cutting edge today. Let's jump right in. So our story kicks off in the 18th century with a real giant of classical physics, a French mathematician, astronomer, and physicist named Pierre-Simon Laplace. This guy was a true genius, working on everything from the theory of probability to the mechanics of the solar system.
So, while he was studying gravity, Laplace came up with an equation to describe fields in empty space. Now think of it like this. He figured out that if you know exactly what's happening on the boundaries of a region, you can perfectly predict the calm, balanced state of everything in the middle. It's a simple but incredibly powerful idea, one that would turn out to have a very long and surprising future.
Okay, so what is this famous equation? What's it all about? Well, even though it's fundamental to physics, its core idea is actually beautiful and simple. It's all about harmony. And here it is. Now don't let the symbols throw you. That little triangle, the delta, is called the Laplace operator. You can think of it as a tool that measures the curvature of a field. Basically, it checks any single point and sees how much it differs from the average of all its immediate neighbors. By setting it to 0, the equation demands that there's no difference. Every point is the perfect average of its surroundings. It describes a state of perfect, smooth equilibrium. Right. A great way to visualize this is to picture a perfectly flat, stretched-out rubber sheet. There are no weights pushing it down, and nothing is poking it up from underneath. That smooth, totally undisturbed surface is what physicists call a harmonic state. Laplace's equation is the mathematical description for fields just like that, perfectly smooth with zero peaks or valleys. Just pure, undisturbed balance. And in the classical world, this idea of harmony shows up everywhere you have a nice, steady, unchanging state. It can describe the electric potential in a space with no charges, or the stable temperature distribution inside an object once it's stopped cooling down, or even the smooth flow of a perfect fluid. It really is the universal equation for equilibrium. Okay, so that's the classical world. Gravity, heat, all things that make sense. Now we're going to take a giant leap into the weird, wonderful, and often counterintuitive world of quantum mechanics. And this is where that old classical equation does something nobody could have ever predicted. You know, at the very heart of the quantum realm, you'll find the Schrödinger equation. It is the absolute master rulebook. It describes something called a particle's wave function, which basically holds all the possible information about its quantum state, and most importantly, its allowed energy levels. And that leads us to the big question. What happens to a quantum particle, like an electron, if it's floating around in a perfectly empty space? A place where there are no electric fields, no forces, nothing pulling or pushing on it, no potential energy at all. What does that quantum master rulebook say about that? And this right here, this is the aha moment. On the left, you see the full Schrödinger equation. It has a term for potential energy, V, and another for the particle's total energy, E. But what happens if there is no potential energy and we look at the absolute lowest energy state? Well, both V and E become 0. The second and third parts of the equation just disappear. And what are you left with? It simplifies directly to Laplace's equation. It's an absolutely incredible connection. In a state of total equilibrium, the quantum rulebook becomes the classical rule for harmony. And this is not just some cool mathematical coincidence you'd find in a textbook.
No way. This is a fundamental engineering principle that physicists are using right now to build actual working quantum computers. Let's take an ion-trap quantum computer, for example. In this setup, your qubit is a single charged atom, an ion. To hold that ion perfectly still, you need to build a tiny, invisible cage made of electromagnetic fields. So, how do you design that cage? First, engineers arrange a set of electrodes. Then, they apply specific voltages to them. Those are the boundaries we talked about earlier. And finally, they use Laplace's equation to calculate the perfectly smooth, harmonic electric field that forms in the empty space between them. The solution gives them this perfect little potential valley that traps a single ion with incredible stability.
And it's not just for ion traps. This same principle is used everywhere. It's used to design the little potential corrals that hold electrons in quantum dots, to figure out the complex electric fields in superconducting qubits, and to create the super clean, noise-free environments you need for quantum sensors. It's really a foundational tool for almost every type of quantum hardware out there today.
And the story is definitely not over. This classic idea of harmony isn't just solving today's engineering problems, it's also helping to shape the very next wave of quantum innovation. So take quantum metrology. That's the science of making ridiculously precise measurements. For things like building better atomic clocks or sensors that can detect tiny gravitational waves, stability is everything. You have to shield your quantum system from any outside noise. And by using Laplace's equation, scientists can design these perfectly harmonic electromagnetic shields, basically creating these pristine, quiet spaces that allow for more precise measurements than we've ever had before. It's even helping us get a handle on some really exotic new materials, like topological insulators. And this is the part I find so cool. The inside, or the bulk of these materials, is often really stable and harmonically smooth. Electrically, it's almost boring. But that perfectly calm interior is exactly what allows these incredibly robust and powerful quantum states to exist right on the material's edge. A boring inside enables an exciting outside, and that's a huge idea for building more reliable, fault-tolerant quantum computers.
Wow, we've really covered a lot of ground, haven't we? We've gone from 18th century France all the way to the quantum labs of the 21st century. So let's take a breath and recap the most important takeaways from this journey. You know, this quote from Jorgo Schneppet's essay just says it all perfectly. This old equation is so much more than a historical relic. He calls it a key instrument for building our quantum future. Its elegance in math is only matched by how incredibly useful it is in the real world today.
So what are the key things to remember? First, a 250-year-old equation for harmony provides a conceptual bridge to quantum mechanics. Second, this link isn't just theory, it's a practical, hands-on tool for engineering the stable environments that qubits need to work. And finally, this timeless idea is still driving innovation today. In a way, an old idea of perfect balance is providing the stable foundation upon which we're building our very complex quantum world.
It really does make you wonder, doesn't it? What other elegant ideas from the classical world are just sitting there, waiting for us to rediscover them and unlock the next quantum breakthrough?
This whole exploration was inspired by the fantastic work of Jorg Schneppet. For more, you can check out his work at schneppet.de. Thanks so much for joining us.
Goodbye!
Schneppet.de is a private project by Jorgo Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.